This week we will be learning about the structure of the atom and the history of how the model of the atom that we will most frequently use in class was developed and what is understood now to be the most accurate and useful model of an atom for our understanding of what's going on with subatomic particles and everything inside of the atom. So we're going to start out by looking at some of these different models. We have over here a little bit more outdated model of an atom. This was contributed by Thomson, and this is called the plum pudding model. And the reason it's called that is because this was the first model that incorporated both positive and negative charges, which we later decided were called protons and electrons. And since there was no real understanding of where protons and electrons were in the atom, he kind of just drew his model as like the positive circle with some negative charges floating around in there. It's kind of like the same idea as like a chocolate chip cookie, but plum pudding was something that people used to eat in that day, so that's why they called it that. Okay. Slightly more advanced from there, we had discovered that there's such thing as mass of an atom and the mass coming from protons and neutrons. And so we have Rutherford's model, which shows the nucleus, which is positively charged and has the mass, with the electrons flying around. These things don't have mass, but we knew they were moving quickly around the nucleus. This was kind of a little bit more advanced concept rather than just the positives and negatives being mixed together. Moving on from there, we have Bohr's model. Bohr's model incorporates not only the nucleus with the positive and neutral charged protons and neutrons, but also now has the electrons around it not in a random movement, but in orbits of different energy levels. And that's what these circles represent, the different energy levels. And so we're going to use the Bohr model actually the most in class because it's the most helpful for, at the high school level, understanding what's going on inside of an atom. And then, even more advanced than that, Einstein and a guy named Schrödinger made a lot of contributions to the understanding that electrons behave actually like light and matter at the same time. And they move in a very unpredictable way, but what you see here with these little lobes are the shapes of orbitals, and they're just basically locations where the electrons could possibly be at some point in time. But it's very, it's impossible to know exactly where an electron is, or it's very difficult to calculate exactly what its energy is. These are just locations where they possibly could be. So it's a little bit more complex, and sometimes you might see it looking a little bit more like a cloud, and that's called the electron cloud model. That's also from the same concept, contributed by Schrödinger and Einstein. Okay, so we're going to use mostly the Bohr model, but when we look at this here, this is kind of somewhere a hybrid between the Bohr model and Schrödinger's model. It kind of looks like a cloud of electrons, but it also shows rings, and these rings represent the energy levels. Okay, so we're going to use this one for discussing the subatomic structure. So the different subatomic particles, I've already mentioned these, are the proton, the neutron, and the electron. And there are things even smaller than these, but these are the ones that we're going to use because that's the most important ones for chemistry's purposes. So the proton has the symbol P+ because protons are positive, and they're located in the nucleus. I didn't put an organization for neutron because neutrons are also inside of the nucleus. Neutrons are neutral, just like the name sounds, which is why we write N with a 0. That represents no charge. They're in the nucleus. And then finally we have electrons, and the symbol for that is E- because electrons have a negative charge, and they're located in the different energy levels. So here we have our nucleus. So like we said before, protons and neutrons are in the nucleus, and so that's why those are labeled. And then out here we have our different energy levels, and the electrons are out there. Okay, So what are the purpose of the different subatomic particles? They each serve their own purpose. They have a role. So to get the mass of an atom, which we've talked a lot about mass, when we talk at the individual atom level, we call the mass units atomic mass units. And these are talking about very small things. But when you are in the lab or whatever, you have large amounts of these substances, so you usually use grams. So they're both talking about mass, they're just different types of units. To get the mass of an atom, we basically can just add up the protons and the neutrons, because each proton and each neutron essentially has a mass of 1 atomic mass unit, or 1 AMU. And that will give us our mass number. So an example of that is down here. We have a carbon atom, and we know that because we can count the neutrons, protons, and electrons, and also it tells us here that it's a carbon atom, but we could have figured that out. If you count the protons, there are 6 protons in the center, and yeah, that's labeled with blue, so the blue ones are our protons. If we were to count them, there are 6, and if we were to count our neutrons, there are also 6. That's the red circles in the nucleus. So to get the mass number, all you have to do is take protons plus neutrons and you get mass. So that's what they did here. 6 plus 6, and they got 12 for the atomic mass. So that's the mass of this atom. You can also figure out the identity of the atom based on the number of protons, which is also called the atomic number. Every single element has its own atomic number, and that is a defining factor for the element, and that's why we call it the identity. So if you look here, we have 6 neutrons in the center, but the neutrons only help us figure out the mass. If we were to count the protons, we could figure out what the identity of the element is, and there are 6 protons. And so I looked on my periodic table and saw that the atomic number 6, or 6 protons, is the element carbon. Then finally, we have charges of our atoms. When you see an atom on the periodic table, if you just assume that the number of protons and electrons are equal, those atoms have no charge. But you could have different numbers of protons and electrons. The proton determines the identity, but if you had fewer electrons than protons, you would have a positive charge, and if you had more electrons than protons, you would have a negative charge. So an example of that's down here. There are 2 protons in this one, so we would plug in 2 here, and you have 3 electrons. So 2 minus 3, that gives you -1. So that's why down here I wrote 2 protons minus 3 electrons equals a -1 charge. So if there are more electrons than protons, you get a negative charge. Then on this one, we have 2 protons with 1 electron out here. So 2 protons minus 1 electron gives you a +1 charge. So if you have less electrons than protons, you're going to have a positively charged atom. And we're about to see what the name of that would be. Okay, some atoms that are not regular, meaning they don't just have equal numbers of protons and electrons, and they may or may not have whatever you would consider to be the most normal amount of neutrons. So something that has a different number of electrons, but the same number of protons, is still the same element, but we call it an ion because it has a charge. Okay, so these two words, ion and isotope. Students confuse these all the time because they both start with I. I don't want you to confuse them. Ion means charged atom. It could be positive or negative. So let's look over here. We have sodium, and sodium has the atomic number 11. So when it has 11 electrons around it, its protons and electrons are equal, and it's neutral. Sodium really likes to lose its outer electron, so when it does that, that means it has less electrons than protons. That means it has more positive stuff than negative stuff, which gives it an overall positive charge. And we could always calculate it by taking 11 protons minus 10 electrons to get plus 1 charge. So that's why I wrote that plus 1 right there. Okay, that's an ion. An isotope is a atom that has the same number of protons, so it's still the same element because its identity has not changed, but you could have a different number of neutrons. So it would have a different mass. And some isotopes are stable and other isotopes are unstable, which is where we get radioactive elements. Okay, so look over here. We have hydrogen. Hydrogen has a mass of 1, and so it also has an atomic number of 1. That means that it has 1 proton but no neutrons. That's how you get a mass of 1. It also has an electron. So since it has the 1 proton and the 1 electron, it has no charge, but it has just the mass of 1. You could also have a hydrogen atom that has a neutron. This one would have a mass of 2 because 1 plus 1 gives you 2. This is called deuterium. This is a very common, well, a somewhat common isotope of hydrogen as well. Hydrogen 1 is the most common. Hydrogen 2 is a little less common, and then the least common would be hydrogen 3, which we call tritium. This has two neutrons and just 1 proton. So the common factor is that all 3 of these have 1 proton, and so that means they're still hydrogen. We just give these special names because we like hydrogen isotopes, and so we think they're special. So these 2 neutrons plus the 1 proton give you a mass of 3. So this is actually a radioactive isotope of hydrogen. So if you were to run into this, it may or may not be a cause of some harmful effect, but it's used for lots of different purposes, such as you may have heard of a hydrogen bomb. Things like that involve hydrogen isotopes, and so this whole concept of isotopes and stability or instability is very important in different applications in the real world. Okay, so moving on. Let's look at an example problem. We have this Bohr model, and I want you to be able to look at it in the number of particles and be able to figure out what atom it is. So if you were to count here, it says that we have 18 neutrons and we have 17 protons. And if you count the electrons, there are also 17 electrons. So, question is, what is the mass? Let's recall that the mass is made up of everything that's inside the nucleus. So if you add these two together, you get the mass. Let's recall that the identity is just the atomic number, or the number of protons. So if we have 17 protons, that's going to tell us what element it is. So if you look at your periodic table, you can probably figure it out before I switch to the next slide. Then finally, if you have the same number of protons and electrons, 17 minus 17, it gives you a charge of 0. If you were to have a different number, you would take protons minus electrons and see what the charge is. So since this is equal, it has a charge of 0, and that means it's not an ion. Okay, it doesn't have any charge. All right, so let's look at our answer here. From the 17 protons, when we look at the periodic table, you get the element chlorine. So remember our identity, 17 protons, atomic number is 17. So if you look at element number 17, that's chlorine. Our mass, it would be from adding together our neutrons and protons, you get a mass of 35. And then finally, like we already said, 17 minus 17, no charge. Okay, so this is a way that you can write the isotope that you have. Remember, isotope just means what's the mass of this element. So we have chlorine, and we know that the atomic number is 17, so you write that down here. The mass number that we got from adding together the protons and neutrons is 35. We could have other isotopes of chlorine, such as isotope 37, which would have a 37 up here that just has 2 additional neutrons. It really depends on which isotope you're looking at. So if I was to get your full answer of what element this is, you should have the mass, the atomic number, the element, and then if there's a charge, you would write that right here. This one does not have a charge. We'll be practicing this in class over the next couple of weeks, but just want to go ahead and expose you to it so you're familiar with it. Thanks.